All right, if you're tackling NCEA Level 2 physics, you know some things can feel like a real headache. Today, we're going to zero in on one of your most important tools, the force diagram. Let's turn this tricky topic into your secret weapon for the exam.
So, let me ask you something straight up. Are you leaving easy marks on the table in your physics exam? Because you know what? So many students do, and it's usually because of tiny, avoidable mistakes on their force diagrams. But here's the good news. This is probably one of the easiest things to fix, and we're going to do it right now.
And that's really the whole story. These diagrams, sometimes called free body diagrams, are one of the biggest sources of what I call easy marks. Getting them right doesn't just score you the point for the diagram itself, it literally unlocks the rest of the question for you.
So, here's our game plan. First, we'll cover the secret to grabbing these easy marks. Then we'll meet the key forces you'll be working with. After that, I'll give you a foolproof 5-step recipe for perfect diagrams. We'll also break down what balanced and unbalanced forces actually mean for motion. And finally, we'll look at the common exam traps so you can sidestep them completely. Okay, let's dive right in. The secret here isn't some crazy complex physics trick. Nope, it's just about understanding one core definition and then sticking to the rules every single time. It all starts with knowing exactly what a force diagram is meant to show. And this is it. This is the foundation. A force diagram shows one object. Just one. We basically pretend it's floating in space all by itself. Then we draw arrows for all the real physical forces acting on that object. No imaginary stuff, no arrows for speed or motion, just the actual pushes and pulls. Get this, and you're already halfway there.
Now, to draw these diagrams, you need to know your players. I like to think of the different forces as a cast of characters that show up again and again in our physics problems. So let's meet the usual suspects for NCEA Level 2.
This is your essential toolkit. Let's do a quick roll call. First up, you've got weight, or FG. It always acts straight down, always. Then you've got the normal force, which is a support force from a surface, and it's always perpendicular to that surface. We've also got tension, which is the pull from a rope, and friction, the force that always fights against motion. An applied force is just any old push or pull. And finally, air resistance, which acts opposite to motion through the air. Knowing this cast is absolutely critical.
So, you know the characters, but how do you put them all together on the stage? You follow a recipe. Seriously, this isn't about guesswork. It's a systematic 5-step blueprint that, if you follow it, will get you a perfect exam-ready diagram every single time.
All right, here's the recipe. Step 1, isolate your object. Just draw a simple dot or a box. Step 2, and always do this first, draw the weight force, Fg, pointing straight down. Step 3, look for anything touching your object. Surfaces, ropes, add those contact forces like the normal force or tension. Step 4, if the object is moving or even just trying to move, add in friction or air resistance pointing in the opposite direction. And finally, step 5, add any other pushes or pulls that the question mentions. Follow those 5 steps in that order and you're golden.
Now, before we move on, let's just burn this golden rule into our brains. You only show forces that are acting on your object. For example, if you have a book on a table and you're drawing the diagram for the book, you draw the table pushing up on the book. You do not draw the force of the book pushing down on the table. That force acts on the table, so it would belong on the table's diagram. It's a super common mistake, but an easy one to avoid.
Okay, so you followed the recipe, you've drawn a perfect diagram. So what? Well, that picture you just created tells a story. It's a visual guide to Newton's laws. It tells you instantly whether the forces are balanced or unbalanced, which in turn tells you exactly what the object's motion is doing.
This slide breaks it down perfectly. On the left, we've got balanced forces. The up forces equal the down forces, the lefts equal the rights. It all cancels out. The net force is 0, so there's no acceleration. Now here's the key bit. That means the object is either at rest or it's moving at a constant velocity. On the right, unbalanced forces. One force is bigger than its opposite. There's a leftover force. This creates a net force, and that net force causes acceleration. The object is speeding up, slowing down, or changing direction.
Let's make this real. Imagine a 5-kilo box just sitting on the floor. Its weight is pulling it down with 49 newtons of force. At the same time, the floor is pushing back up with a normal force of, you guessed it, exactly 49 newtons. They perfectly cancel out, the net force is 0, the box doesn't move. In your diagram, the up and down arrows would be the exact same length.
But now, what if we push that same box to the right with 10 newtons?
Suddenly things are unbalanced. The vertical forces are still balanced, but horizontally we have a 10-Newton force with nothing pushing back. There's a net force to the right. Your diagram would clearly show this longer arrow, and thanks to F equals ma, that net force is what causes the box to accelerate. The diagram makes it totally obvious why it's accelerating.
All right, time for the pro tips. We've got the foundation down. Now let's talk about the common mistakes people make when the pressure is on in an exam. Knowing what these traps look like is the best way to make sure you don't fall into them. You would not believe how often this happens. Seriously, a student sees a box on a table and they just forget about gravity. But gravity doesn't just switch off. It's pretty much the one force that's in almost every single problem you'll ever face on Earth.
And the fix is so simple. Just make it a habit. The very first arrow you draw on any force diagram, no matter what, is the weight force, Fg, pointing straight down. If you make that your automatic first move, you'll never forget it again.
Okay, this next one is a huge conceptual trap. A student sees an object is moving to the right, so they draw an arrow pointing right and label it motion. But motion isn't a force. Velocity isn't a force. Motion is the result of the forces. Drawing a motion arrow is a guaranteed way to lose marks.
The solution here is to go back to our cast of characters. Only draw real pushes and pulls. If you can't give it a proper force name, like weight or tension or friction, then it does not belong on your diagram, period.
So many of us are taught that the normal force always points straight up. And that's true, but only on a flat horizontal surface. The second you put your object on a ramp or an inclined plane, that idea becomes a trap. And if you get the direction of this force wrong, the whole problem becomes impossible to solve.
Here's the key. The normal force is called normal for a reason. In math and physics, normal means perpendicular, or at a 90-degree angle. So the normal force always points 90 degrees away from whatever surface the object is sitting on. Remember that, and ramps will never scare you again.
All right, to pull this all together, I want to leave you with a really powerful tool. Think of this as your final pre-flight checklist, the thing you quickly run through in your head during an exam before you move on from a force diagram question. Just ask yourself these quick questions. Is my object isolated? Check. Have I gone through my mental toolkit of forces? Weight, normal, tension. Check. Is every arrow labeled correctly? Are the directions right? Weight down, normal perpendicular? And here's the big one. Does my diagram actually match the motion in the question? A balanced diagram for something that's speeding up is a huge red flag. And one last little check. Did I remember to convert my mass in kilograms into a weight in newtons? If you run through this quick checklist every time, you're not just drawing a diagram, you're proving you understand the physics. Because the real test isn't can you draw some arrows, it's do you understand the story that your diagram is telling?